There was a time when the entire universe was brighter than the surface of any star. An impossible paradoxical thought, isn't it? We are creatures of light and shadow, conditioned to believe that brilliance is born from celestial fire. Yet the story of our cosmos begins not with a spark, but with a blinding, all-encompassing inferno. And this primordial glare, this searingly hot genesis, was the direct ancestor of the most profound, the most absolute and enduring darkness the universe has ever known. To understand this, to truly feel the weight of that immense night, we must travel back, not just through human history past the reach of our telescopes, but beyond the familiar shores of our own galaxy. We must undertake a journey to the very edge of time itself. Imagine yourself adrift in the cosmic ocean, the Milky Way, a brilliant swirling disk behind you. Now we accelerate, pushing backward through the eons. Galaxies like Andromeda, once majestic neighbors, shrink into faint smudges of light and then vanish. We fly through the Hubble Deep Field, a tapestry woven from the light of 10,000 galaxies, each a city of 100 billion suns, each with its own story, its own worlds, its own possibilities. But for us, this is just a milestone on a much longer road. We push deeper, faster, rewinding the cosmic clock. The galaxies themselves begin to change. They grow smaller, more chaotic, more intensely blue. These are the toddlers of the cosmos, furiously assembling themselves from rivers of pristine gas. The elegant spirals and grand ellipticals of our own time are nowhere to be seen. Here in the deep past, there is only the frantic energy of creation, a violent and beautiful adolescence. We pass the light of the most distant quasars, the beacons of the young universe. These are the tormented hearts of the first great galaxies, powered by supermassive black holes, feasting on unimaginable quantities of matter, shining with the light of 1 trillion stars combined. They are the lighthouses of the cosmic dawn, but we must journey past them, into an age before their ferocious light ever had a chance to pierce the gloom. Faster and further we go, crossing a gulf of 1 billion years, then 2, then 5, then 10. The universe grows denser, hotter, and stranger with every moment we reclaim from the past. The space between galaxies collapses. The cosmic web, that vast filamentary structure of dark matter that organizes the universe, has not yet had time to fully weave itself. Everything is closer, more compressed, more intimate. The light from the objects around us becomes redder and redder, the expansion of space we are reversing, stretching their wavelengths to their very limits. Finally, we push past the final frontier of observation, beyond the faintest, oldest galaxy we have ever seen. We are now in a time and a place that no telescope will ever witness directly. We are entering the era before galaxies, the age before stars, and here, approximately 13.8 billion years ago, we arrive in a universe that is utterly alien. It is not dark. It is not empty. It is a furnace. The entire cosmos, from one edge of infinity to the other, is a single unified incandescent plasma. A seething, tumultuous soup of fundamental particles crushed together under impossible pressures and heated to temperatures of thousands of degrees. There are no atoms here, not as we know them. The heat is so intense that electrons are ripped away from protons, forced to exist as a free chaotic swarm. And this is the key to that ancient paradox. In this primordial state, the universe was perfectly opaque. Light in the form of photons was trapped in a furious cosmic pinball machine. A photon could travel no more than a fraction of a millimeter before slamming into a free electron, ricocheting in a random direction, only to strike another and another in an endless violent dance. Imagine trying to see through the very core of our sun. You cannot. The light is there, generated by nuclear fusion, but the plasma is so dense that it takes 100,000 years for a single photon to stagger its way to the surface. Now take that state of matter, that impenetrable wall of light and energy, and expand it to fill the entire observable universe. That was our cosmos for its first 3,800,000 years. A brilliant, featureless, inescapable fog, a prison of light. No information could propagate, no structures could form, no story could yet be written. It was a universe filled with light but utterly devoid of sight, a brilliant, blinding darkness. But the universe from its very first moments has been a story of change, of transformation. It was expanding, and as it expanded, it cooled, slowly, inexorably, second by second, year by year. The frantic energy of that primordial plasma began to wane. The particles slowed their dance, the temperature dropped, and as the cosmos approached its 380th birthday, it crossed a critical magical threshold. The temperature fell just low enough for the relentless electromagnetic force to finally win its long war. For the first time, the attraction between protons and electrons became stronger than the violent thermal energy that had kept them apart for so long. An event of profound and universe-altering significance began to sweep across the cosmos. It is an event we call recombination. One by one, then, in a cascading thunderous wave, free electrons were captured by lonely protons. The first atoms of hydrogen were born, a simple, elegant union of two particles that would change the destiny of everything, because with every electron captured, one less obstacle stood in the way of the trapped photons. With every atom formed, a tiny window opened in the cosmic fog, and as this process completed in a geological and cosmological blink of an eye, the entire universe underwent a stunning transmutation. From opaque, it became transparent. And in that instant, all of the light that had been trapped for millennia was suddenly gloriously set free. A flash of unimaginable brilliance released simultaneously from every single point in space. The last gasp of the primordial fireball, the universe's first and greatest sunset. This light, this final fading echo of our cosmic birth, began its own immense journey. A journey of 8 billion years through the expanding, evolving, and darkening cosmos, to eventually fall upon the sensitive instruments of our modern telescopes. We know it today as the cosmic microwave background radiation, the CMB. When we map this light across the entire sky, we are looking at the oldest photograph in existence. It is the baby picture of our universe, an image taken when it was just a newborn infant. And it is without question the most important single piece of evidence in all of cosmology. It tells us so much. Its temperature, now cooled by cosmic expansion to a mere 2.7 degrees above absolute zero, confirms the Big Bang theory with breathtaking precision. It is a message from a time when there were no planets, no stars, no galaxies, nothing but a cooling gas. To our eyes, this ancient light appears almost perfectly uniform, a smooth, even glow in every direction. A testament to a universe that began in a state of near-perfect simplicity. But hidden within that smoothness, encoded in its very fabric, are clues of unimaginable importance. For the CMB is not perfectly uniform. If we amplify its signal, we can see tiny, almost imperceptible variations in its temperature. Faint ripples, splotches of slightly warmer and slightly cooler regions differing by only 1 part in 100,000. They seem like noise, like random imperfections in an otherwise flawless picture, but they are anything but. These minuscule fluctuations are the seeds of everything that would ever come to be. They are the fossilized echoes of quantum jitters from the first trillionth of a second of the Big Bang, magnified by cosmic inflation to astrophysical scales. These subtle variations in temperature correspond to subtle variations in density. The slightly cooler, denser patches were the locations of infinitesimally stronger gravity. They are the first whispers of structure, the faded architectural blueprint for the entire grand cathedral of the cosmos. Here, a supercluster of galaxies would one day form. There, a great void of cosmic emptiness would expand. And in one of these unassuming, slightly denser regions, the seeds of our own Milky Way galaxy were sown. All of it, every star, every planet, every one of us, owes its existence to these faint, ghostly ripples in the oldest light in the universe. This light represents a profound boundary in our knowledge. It is the edge of the visible. We can build more powerful telescopes, peer deeper into space and further back in time, but we can never ever see past the moment this light was released. The universe before it was an opaque wall. This is the farthest back our eyes will ever be able to look. And with its release, a great curtain fell upon the stage. The primordial fireball was gone. Its light, now the CMB, was released, and flying away, its energy dimming, and its wavelength stretching with every passing moment as the universe expanded. The cosmic stage was now transparent, yes, but it was also empty. There were no new sources of light to replace the old. No stars had yet been lit. No galaxies had yet been gathered. The universe, for the very first time in its history, plunged into a deep, pervasive, and absolute darkness. This was the beginning of the cosmic dark ages. It was a darkness of a kind we can barely comprehend. It was not the simple darkness of a moonless night punctuated by the distant glow of cities or stars. This was a perfect, untainted blackness. The only light that existed was the fading afterglow of the Big Bang, which quickly redshifted beyond the visible spectrum, becoming a ghostly, invisible hum. For a mind's eye floating in this abyss, there would be nothing to see. Absolutely nothing. Only the cold, the silence, and the patient, unending night. The universe was now a simple, almost featureless place. A vast, expanding cosmos filled with a thin, uniform fog of neutral hydrogen and helium gas. Beneath it all, supporting it and guiding it, was the invisible scaffolding of dark matter which had already begun to slowly draw together under its own gravity. But for now, everything was diffuse. Everything was dark. This period of darkness was not fleeting. It was not a brief intermission. It was an entire chapter of our cosmic story. It lasted for an almost unimaginable length of time. 100 million years, 200 million years, perhaps even longer. The exact duration is one of the great frontiers of modern astrophysics. Think of that. For hundreds of millions of years, the universe was a place without a single star. The entirety of recorded human history is a mere 5,000 years. The age of the dinosaurs lasted for 165 million years. The cosmic dark ages persisted for longer than the dinosaurs ruled the Earth. It was an epoch of profound quiet and stillness, an era of waiting. A long, cold and silent night. Yet this was not an empty or a wasted time. The darkness was not a void. It was a womb, for within that profound blackness the most important construction project in the history of the universe was underway. The silence was deceptive, because gravity, the patient, relentless architect of the cosmos, never sleeps. Those tiny, almost insignificant density fluctuations we saw imprinted on the cosmic microwave background, they were now the only game in town. They were the kernels around which everything would coalesce. The regions of space that were ever so slightly denser began to exert an ever so slightly stronger gravitational pull. It was a process of excruciating slowness, a cosmic ballet choreographed by the weakest force in nature. The invisible halos of dark matter, immune to the forces that governed light and regular matter, acted as the great gravitational anchors. They began to slowly, patiently draw in the surrounding clouds of hydrogen gas. Over millions upon millions of years, these clouds were pulled from the expanding void, streaming along the invisible filaments of the cosmic web, converging on the growing nodes of dark matter. Countless tons of hydrogen drawn together molecule by molecule, atom by atom. The clouds grew denser, the gravitational pull grew stronger. A feedback loop of creation was beginning, hidden deep within the impenetrable darkness. In thousands of locations across the vast expanse of the young cosmos, these pristine clouds of gas were reaching a tipping point. They were compressing, heating up their cores, growing ever more crowded. The universe was pregnant with a new possibility. It was on the verge of inventing something entirely new. It was about to invent the star. And this brings us to the great central mystery of this lost age. It is the question that drives our journey into this primordial night. How did this process unfold? How did a universe of cold, dark, featureless gas transform itself into the brilliant star-filled cosmos we know? What was the spark that finally ended the long night? How precisely did gravity gather that first handful of hydrogen and compress it so intensely that it ignited the fires of nuclear fusion for the very first time? What were those first stars, the mythical population 3 stars, actually like? These were the true pioneers. Titans forged from the pure, unpolluted material of the Big Bang itself. Their lives, we believe, were violent, brilliant, and short, and their deaths seeded the universe with the heavy elements necessary for planets and for life. They were the agents of a second great transmutation. Their light didn't just illuminate the darkness, it shattered it. Their radiation ripped apart the neutral hydrogen atoms that had dominated the universe for so long in an event we call reionization, a cosmic dawn that cleared the fog and set the stage for the modern era. To understand our own origins, to grasp the story of our galaxy, our sun, and our planet, we must first understand this hidden epoch. We must venture into the darkness. We must search for the faint fossilized clues left behind by these first lights. This is a detective story on a cosmic scale. Our challenge is to reconstruct a chapter of history that was written in a language of shadow whose pages were erased by the very dawn it created. How did the universe make light? How did the cosmos, after hundreds of millions of years of slumber, wake up? How does a universe born from an explosion of pure, unimaginable light fall into an epoch of absolute unbroken darkness? It's a paradox that lies at the very heart of our cosmic story, a chapter written not in fire but in an all-consuming fog. To understand it, you have to travel back with us, back to a time when the entire cosmos was younger than a single human heartbeat, is to the grand sweep of history. Imagine an infant universe just 380,000 years old. It is not the cold, structured place we know today. Instead, it is a tempest, a howling, searing plasma, where the fundamental building blocks of matter are locked in a chaotic war. Protons, the hearts of future atoms, and electrons, their elusive partners, are torn apart by the sheer incandescent energy of the moment. They are a charged, frenetic sea, and swimming through this sea are the photons, the particles of light themselves. But in this primordial state, light cannot know freedom. Every time a photon attempts a journey, it immediately collides with a free-roaming electron careening off in a new direction, like a ricocheting bullet in a hall of mirrors. The universe is perfectly opaque, not because it is dark, but because it is blindingly, chaotically bright. It is a star, but one that fills all of space, a furnace with no outside. Every point in the cosmos is the center of an explosion of light that has nowhere to go. This was the state of things for hundreds of thousands of years, a brilliant, frantic, and ultimately formless age. The fundamental forces were at play. Gravity was beginning to whisper its intentions to the slight unevenness of the cosmic soup, but the universe was trapped, locked in a prison of its own energy. It was waiting for a change. It was waiting to cool. And then, as the tireless engine of expansion continued to stretch the very fabric of space-time, a critical threshold was crossed. The universe's cosmic fever finally broke. The temperature dropped not to a level we would call cool, but to a mere few thousand degrees, just gentle enough for the long-delayed alchemy to begin. For the first time, the frantic energy of the cosmos was no longer strong enough to keep proton and electron apart. A profound and universe-altering event known as recombination began to unfold. Across the entirety of existence, the frenzied dance of opposition ceased. A proton, with its powerful positive charge, could now finally capture a passing electron, binding it in an orbital embrace. An atom was formed, a simple neutral atom of hydrogen. This was not a rare occurrence. It happened everywhere, all at once, a quiet collective sigh of a universe transitioning from chaos to structure. This single act of cosmic union, repeated trillions upon trillions of times in every direction, fundamentally rewired the nature of reality. The change was instantaneous and absolute. With the free-roaming electrons now captured, safely orbiting their proton partners, the universe's legion of trapped photons found their paths suddenly miraculously clear. The fog of charged particles that had scattered them for millennia simply vanished. The mirrors dissolved, and so, in a silent, magnificent flash that filled the entirety of space, light was set free. Every one of those photons at that exact same moment began a journey, an arrow shot from the bow of creation into the future. They have been traveling ever since, a ghostly fading echo of that first singular moment of clarity. This is the light that we see today when we look beyond the galaxies, a faint, cold glow in the microwave spectrum. It is the cosmic microwave background, the CMB. It is the most important photograph ever taken, for it is nothing less than a picture of our universe at the moment of its birth as a transparent entity. It is a baby picture of the cosmos, a fossilized remnant of the final instant of incandescent heat before the Great Change. In its subtle variations of temperature, we can read the faint whispers of quantum fluctuations from the Big Bang itself, the tiny seeds from which all future galaxies, all stars, and we ourselves would one day grow. You are looking at the afterglow of creation, the last light. For as this final glorious wave of photons began its eons-long journey across space-time, the very agent of its liberation was preparing to draw a curtain across the cosmos. The neutral hydrogen that had so beautifully cleared the way for the CMB was about to become the universe's new gatekeeper, its new prison warden. The era of light was over. The Dark Ages had begun. The universe, now transparent to that ancient stretching light of the CMB, was simultaneously becoming completely opaque to any new times light that might be generated. Think of it not as a wall, but as a fog thicker and more pervasive than anything imaginable on Earth. This fog was made of those newly formed neutral hydrogen atoms. While a single atom is mostly empty space, their collective presence on a cosmic scale changed everything. A neutral hydrogen atom is tuned like a celestial radio to absorb photons of very specific energies, particularly the energetic ultraviolet light that young hot stars would one day produce. Before the first stars were born, there was nothing to see, but the conditions were now set. Any future light source would find itself entombed. A nascent star, were it to somehow ignite in this environment, would be like a candle lit inside a mountain of black dust. Its light would travel mere inches before being absorbed by a hydrogen atom. Its energy captured its journey, ending almost before it began. The universe had traded one form of opacity for another. It had exchanged the brilliant hot fog of a plasma for a cold, dark, and deeply absorbing shroud of neutral gas. The last visible light, the CMB, continued to stream away from every point, its wavelength stretching and cooling as the universe expanded, fading from a brilliant golden glow to a dim cherry red, then to infrared, and finally into the invisible microwaves we detect today. Behind it, it left nothing, a void. Not a void of matter, for the universe was full of hydrogen and helium gas, and the invisible scaffolding of dark matter was already beginning to pull this gas into great ghostly filaments. But it was a void of light, a silent, starless, galaxyless expanse, utterly and completely black. The cosmic stage was set, the raw materials were all present, but the lights had been turned off and the actors were not yet ready. To speak of the timescale of this epoch is to confront a span of time that humiliates human comprehension. This was not a brief intermission. The Dark Ages lasted for hundreds of millions of years. Let that number settle in. The entire recorded history of our species, from the first cave paintings to the rockets that pierce the sky, is a mere few thousand years. The dinosaurs roamed the Earth for over 150 million years, an immense reign that we struggle to truly grasp. The cosmic Dark Ages lasted longer than the entire age of the dinosaurs, perhaps twice as long, maybe even longer. For an unbroken, seemingly infinite stretch of time, the universe was a place of profound simplicity and patience. Imagine it, an ocean of hydrogen and helium gas cooling slowly in the dark. The faint, ever red-shifting ghost of the CMB is the only energy of note. The tendrils of dark matter themselves, completely invisible, are the only architects patiently, silently, gravitationally herding the primordial gas into denser and denser regions. There are no planets, there are no suns, there is no stellar fire, no fusion, no starlight reflecting off the surfaces of majestic, swirling gas giants. There is no life, no consciousness to witness the immense patient stillness. There is only the cold, the dark, and the inexorable, impossibly slow pull of gravity. It is the ultimate blank slate. If you could stand on a precipice in that universe, your eyes would detect nothing. Not a single point of light in any direction. The darkness would be absolute, a perfect Stygian blackness that our modern light-polluted skies can only hint at in our wildest dreams. The silence, too, would be absolute, broken only by the faint hiss of the cooling background radiation and the whisper of gravity drawing the cosmos toward its next violent and glorious chapter. This is the great enigma we face. All of our astronomy, all of our understanding of the cosmos is based on gathering light. Telescopes are merely buckets for collecting ancient photons. But how do you study a time when there was no light to collect? How do you map a territory that was by its very nature invisible? How do we pierce a veil woven from the very fabric of the early universe? This is the profound challenge that faces cosmology. We have a baby picture of the universe, the CMB, and we have the sprawling family albums of the modern cosmos filled with teenage and adult galaxies. but the entire childhood and adolescence of the universe is missing. The story of how those tiny faint seeds in the CMB grew into the first gargantuan luminous structures is a chapter that was written in the dark. For decades it was considered a lost chapter, a part of our history that was fundamentally unknowable, forever sealed behind that impenetrable fog of hydrogen. We were like archaeologists who had found the blueprints for a cathedral and the cathedral itself, but had no idea how the stones were carved, lifted, and set in place. But science is relentless in its pursuit of the unknown. We have begun to understand that even in this absolute darkness there were whispers. The darkness itself, it turns out, was not perfectly uniform. The very gas that formed the shroud held clues within it, secrets that could be unlocked not by looking for light, but by listening for a very specific kind of cosmic silence. The story was not lost merely hidden, waiting for us to invent new ways, to see new senses, to probe the vast dark emptiness. The challenge is to find the ghosts of these first structures, the subtle gravitational footprints they left on the matter around them. We must learn to read the shadows, to reconstruct the first chaotic, violent, and world-breaking events that finally, after hundreds of millions of years of darkness, would begin to tear holes in the cosmic fog, allowing the first light, the first stars to finally blaze forth and end the long night. The story of that first dawn is where our journey must take us next, and so the great cosmic silence descended. A quiet so profound, so absolute it would stretch across hundreds of millions of years, a seemingly eternal pause in the universe's grand symphony. The aftermath of creation's fever had cooled into a featureless, starless expanse, a kingdom of neutral hydrogen and helium gas adrift in an ocean of impenetrable black. But to believe that nothing was happening in this lightless epoch would be a profound mistake. For in the dark, where eyes are useless, other senses, other forces begin to dominate. The universe was not sleeping, it was waiting, it was building, and the architect of this new phase of creation was a substance we had only just begun to comprehend, a ghostly presence that had been with us from the very beginning. It was the universe's invisible majority, the quiet and unassuming powerhouse known as dark matter. This was its time to shine, or rather to act without shining. While ordinary matter, the stuff of you and me, and the gas filling the void, was still reeling from its battle, with light pushed and pulled by the intense radiation of the early cosmos, dark matter felt none of it. Photons, the very carriers of light and energy, passed through it as if it were nothing more than a phantom. It was and is the ultimate wallflower at the cosmic dance, uninterested in the electromagnetic swirl of charged particles. It had only one master, one allegiance: gravity. And in the uninterrupted quiet of the Dark Ages, the patient, relentless whisper of gravity was the only law that mattered. This was the secret engine, turning silently in the dark, poised to construct the very foundations of the world we know. Imagine trying to build a celestial cathedral in a hurricane. That was the challenge for ordinary matter. The storm of photons in the early universe was too violent, scattering protons and electrons, preventing them from gathering, from settling down. But dark matter was immune to this storm. It felt no photonic wind. Long before the cosmos became transparent, while normal matter was still trapped in that glowing plasma, the dark matter had already begun its slow, deliberate work. It was free to respond to the faintest, most ancient of instructions, the subtle imperfections forged in the very first moments of time. These were not grand sweeping commands, but minuscule variations in density, tiny regions where by sheer chance there was just a fraction more substance than elsewhere. In a perfectly smooth universe, gravity would have no purchase, no starting point. But our universe, thankfully, was not perfect. These primordial seeds, infinitesimally small, became the focal points for dark matter's grand project. Where there was slightly more mass, there was slightly more gravity. That gentle pull acting over eons began to coax yet more dark matter into the fold. The process was agonizingly slow, a gravitational accretion happening on a scale almost beyond human conception. It was not a collapse, it was a congregation, a quiet, purposeful gathering in the endless dark. Think of it as the formation of an invisible skeleton. While the flesh and blood of the cosmos, the hydrogen and helium, was still a formless, free-floating fog, dark matter was meticulously laying down the bone structure. the girders and beams upon which everything else would eventually be built. It was creating the gravitational basins, the gentle depressions in space-time that would one day become the cradles for galaxies. Crucially, the nature of this mysterious substance was paramount. Cosmologists theorize about different flavors of dark matter distinguished by their speed. If dark matter were hot, composed of particles moving at near the speed of light, this delicate construction project would have been impossible. Hot dark matter particles would simply zip past one another, their immense velocities overpowering the feeble gravitational pull of the early density fluctuations. Structure, if it formed at all, would have done so from the top down, with enormous galaxy cluster-sized sheets, forming first and then fragmenting later. But this is not the universe we observe. Our cosmos is built from the ground up. The evidence points instead to cold, dark matter, a sea of slow-moving heavy particles. These particles, whatever they may be, WIMPs, axions, or something so exotic we have yet to even name it, were sluggish enough to be captured by those initial faint gravitational seeds. They were capable of clumping together on small scales, first forming what we call halos, small spherical clouds of invisible mass. These were the first true structures in the universe. Not stars, not galaxies, but humble invisible halos of dark matter, ranging from the mass of a star cluster to that of a small galaxy. They grew like gravitational snowballs rolling downhill. A small halo would form its gravity, pulling in more dark matter, making it larger and more massive. Nearby halos would feel each other's pull, slowly drifting together over millions of years before merging in silent phantom collisions to create an even larger halo. This hierarchical assembly, this bottom-up model of structure formation, is the cornerstone of modern cosmology. It was happening everywhere in the dark, a slow-motion ballet of billions of these invisible objects clustering, merging and growing, dictated solely by the pull of their own collective mass. The universe was weaving its own dark tapestry, a network of interconnected filaments and nodes, a cosmic web whose existence was known only to gravity itself. But how can we possibly know this? How can we map a construction project that was completed in total darkness, carried out by an invisible workforce hundreds of millions of years before the first star ever ignited? The answer lies in a fossil, an echo from an even earlier time. We must look back to the very moment the universe became transparent, to the faint, lingering afterglow of the Big Bang, the cosmic microwave background. When we first discovered it, it appeared impossibly uniform, a smooth canvas of light from every direction. It was the picture of a universe in its infancy, a cosmic baby photo of stunning simplicity. But as our instruments grew more and more sensitive, capable of discerning the faintest of details, we found that the canvas was not so smooth after all. Hidden within that uniform glow are tiny, almost imperceptible variations in temperature. Patches of the sky that are 100,000th of a degree warmer or cooler than the average. These are not random noise. They are the most important message ever received a Rosetta Stone for the entire history of the cosmos. These minuscule temperature fluctuations are a direct snapshot of the density fluctuations in the primordial soup. The slightly cooler blue spots on our CMB maps correspond to regions that were slightly denser. The slightly warmer red spots are regions that were slightly less dense. And here is the crucial connection. These denser regions, these seeds of structure, exerted a stronger gravitational pull. They were the very places where cold, dark matter had already begun, its patient work gathering into the first small halos even before this light was released. The CMB is not just a picture of the early universe. It is a ghost image, a faint gravitational blueprint of the dark matter scaffolding that was already taking shape. The photons of the CMB reveal where the ordinary matter was, but they also betray the presence of the dark matter that was pulling on it. In those slightly denser regions, as the gas fell into the shallow gravitational wells carved out by the dark matter, it was compressed and heated. As it bounced back out, it cooled. This cosmic symphony of gravitational pull and radiation pressure left its indelible imprint on the light we see today. Those tiny temperature spots are the fossilized sound waves that once echoed through the infant cosmos, and their precise size and distribution tell us a remarkable story. They tell us exactly how much dark matter there was, how much normal matter, and what the initial conditions were. They provide the starting parameters, the initial code for the entire universe. They are the ultimate forensic evidence. With this evidence in hand, we can do something truly extraordinary. We can create a universe in a box. Using the world's most powerful supercomputers, cosmologists can run what are known as N-body simulations. They take the precise ingredients measured from the cosmic microwave background, the amount of dark matter, the size of the initial density ripples, and place them into a simulated expanding cosmos. They program in a single law, the law of universal gravitation. Then they press run and watch what happens. What unfolds on the screen is nothing short of a miracle. The simulation begins with a nearly uniform distribution of virtual dark matter particles mirroring the infant universe. But under the relentless influence of their own simulated gravity, the particles slowly, inexorably begin to drift towards the slightly denser regions. Over billions of simulated years, we watch the Dark Ages unfold. We see the first small halos form just as theory predicts. We see these halos merge, growing larger and larger. Gradually, a stunning and familiar structure begins to emerge. The dark matter doesn't just clump randomly. It arranges itself into a vast, intricate network of filaments, walls, and voids. The filaments are like colossal cosmic rivers, channeling dark matter from the empty regions, the voids towards the intersections. And at these intersections where the filaments meet the largest, most massive halos congregate, forming vast clusters. We see the cosmic web being woven before our very eyes. The silent, invisible architecture of the Dark Ages is revealed in breathtaking detail. It is a ghostly skeleton of a universe waiting for its stars. The profound, awe-inspiring moment comes when we compare the final state of these simulations to the universe we see around us today. When astronomers map the locations of millions of real galaxies in the local cosmos, they uncover a structure, a cosmic web, a network of filaments, walls and voids with galaxies clustered at the intersections of the great filaments. The resemblance is not just close, it is statistically perfect. The computer-generated universe, born from the initial conditions of the CMB and guided only by gravity, evolves into a structure that is indistinguishable from the observed large-scale structure of our own universe. This is how we know. This is how we part the curtains of the Dark Ages. The simulations anchored by the hard data of the CMB provide an airtight case. They are our time machine, allowing us to witness the invisible work that laid the groundwork for everything. So while the universe was dark to any potential observer, it was far from dormant. A vast, silent construction project was underway. The dark matter halos, these invisible gravitational anchors, were growing ever more massive. Having spent millions of years gathering their own kind, they were now beginning to exert an undeniable influence on the rest of the cosmos. The ordinary matter, the endless clouds of hydrogen and helium, had been drifting aimlessly since the universe turned transparent, but it too feels the pull of gravity. Slowly at first, but with gathering conviction, this primordial gas began to answer the call of the dark matter halos. It began to fall into these deep, invisible wells in space-time. The process was like a slow rain falling from all directions into a multitude of unseen valleys. The hydrogen and helium gas, which makes up nearly all of the visible matter in the universe, was being drawn towards these centers of dark matter concentration. As it fell, it began to pool to accumulate in the very heart of the halos. For the first time since the Big Bang, ordinary matter was being systematically collected and concentrated into dense, compact regions. The scale of this process is immense. Imagine clouds of gas larger than entire star systems pulled over millions of light years to a common center. The two primary constituents of the universe, the visible and the invisible, were finally coming together. The dark matter had built the cities, and now the inhabitants, the hydrogen and helium gas, were beginning to move in. Within the core of each dark matter halo, a transformation was beginning. As more and more gas poured into the gravitational well, it had nowhere to go. It was compressed, squeezed by the relentless pull from all sides. The density of the gas began to climb from near-perfect vacuum to something far more substantial. And as any gas is compressed, it heats up. The silent, cold Dark Ages were developing pockets of rising heat and pressure hidden deep within the dark matter cocoons. The stage was now meticulously set. The invisible scaffolding had been erected, a grand cosmic web stretching across the void. The raw material, the hydrogen and helium fuel of the cosmos, had been gathered and concentrated within the nodes of this web. Everything was in place. The universe had spent nearly 400 million years in darkness, patiently arranging the pieces for its next great act. The quiet was about to be broken. In the cores of the densest halos, the compressed gas was approaching a critical threshold, a point of no return. The pressure and temperature were climbing to levels not seen since the first few minutes after the dawn of time. A new force, long dormant, was about to awaken deep within these primordial clouds. The universe was holding its breath on the precipice of a violent and spectacular transformation. The long night was nearly over. The darkness had done its work, setting the stage for a new kind of creation, one that would banish the shadows and fill the cosmos with brilliance. A fire was about to be lit, and so for 200 million years the universe held its breath. Inside those immense invisible halos of dark matter, the patient work of gravity continued its silent, relentless masterpiece. The primordial gas, that pure and simple mixture of hydrogen and helium, was being drawn inward, pulled from the cosmic web into ever denser concentrations. Think not of a gentle stream, but of an ocean of gas, a diffuse and ghostly sea slowly draining into 1,000, 1,000,000, 1,000,000,000 unseen whirlpools scattered across the infinite dark. Each halo was a gravitational seed, a cradle waiting for a miracle. As the gas fell inward, it began to heat up, a consequence of the simple physics of compression. A cosmic bicycle pump squeezed on a scale that defies all human intuition. Yet this process was fundamentally different from the star formation we see today. For this pristine gas was missing a crucial ingredient, a catalyst that makes the birth of stars like our sun possible. It was missing dust, it was missing carbon, oxygen, silicon, iron. It lacked any element heavier than helium, the very materials that in the modern universe act as efficient coolants. These heavier elements are like microscopic radiators, allowing a collapsing gas cloud to shed its heat fragment into countless smaller clumps and form a bustling stellar nursery of thousands of stars. But here, in the utter purity of the beginning, there was no such escape valve. The collapsing cloud of hydrogen and helium had no easy way to cool down. It was a runaway process, a gravitational chain reaction with no internal break. The entire colossal mass of gas within a halo, hundreds of thousands of times the mass of our own sun, was fated to collapse not into a glittering city of stars, but toward a single monstrous solitary point. Imagine being there, a disembodied observer in the heart of one of these protogalactic nurseries. The darkness is absolute, but the pressure is a palpable force. The gas grows thicker, not yet a solid, but a terrifyingly dense fog, a fluid medium where atoms are jostled together with increasing violence. The core of this collapsing behemoth becomes a crucible of unimaginable intensity. The temperature climbs past thousands, then tens of thousands, then millions of degrees. Gravity is squeezing this primordial matter with a force so total, so focused, that the very nature of reality is about to be rewritten. For eons, the only forces at play were gravity and the expansion of space-time itself. But now, deep within this suffocating core, a new power is about to be unleashed. The protons of hydrogen atoms, the universe's most basic building block, are being forced together against their fundamental electrical repulsion. The fight is titanic. For every million years of slow, agonizing compression, there comes a final moment of surrender. A point is reached, a threshold of temperature and density so extreme that the electromagnetic force which keeps positively charged protons apart is finally and utterly overwhelmed by the strong nuclear force. In that instant, in a flash of pure energy that banishes the dark for the first time in cosmic history, 2 protons fuse, and then 2 more, and then trillions upon trillions more in a self-sustaining explosive chain reaction. A heart of fusion ignites. The first star is born. This is not the gentle dawn you might imagine. This is a violence of creation, a thermonuclear detonation contained only by its own immense gravity. It is a scream of light, a declaration of war against the eternal night. We call these first magnificent monsters Population 3 stars. The name is a historical quirk of astronomy, but it perfectly suits their almost mythical status. They were nothing like our Sun, that calm yellow dwarf which has gently warmed our world for billions of years. A population 3 star was a Titan, a celestial aberration. Born from that inefficient cooling process, they were colossal, easily containing the mass of several hundred of our suns packed into a single cohesive sphere. Their purity, their composition of only hydrogen and helium, meant their cores burned at temperatures we can barely comprehend. Consequently, they didn't shine with a familiar yellow or even a crisp white light. They blazed with an incandescent violet-white fire, a light so energetic it consisted mostly of hard ultraviolet radiation, a celestial blowtorch that would sterilize any nascent world in an instant, and they were ephemeral. The rule of stars is simple and brutal. The bigger they are, the faster they burn. A star hundreds of times more massive than our Sun does not live hundreds of times longer. It lives thousands of times shorter. Its immense gravity crushes its core with such ferocity that it burns through its vast supply of hydrogen fuel, not in billions of years, but in a mere 2 or 3 million. They were the universe's ultimate pioneers, living fast and dying young, but in their fleeting existence, they would change everything. The light from this very first star now floods its cradle. For the first time, we can see the structure of the dark matter halo it inhabits illuminated from within. The star's radiation, a furious gale of high-energy photons, slams into the surrounding neutral hydrogen gas, that pervasive fog that has defined the Dark Ages. This is the beginning of a process we call reionization. The photons are so energetic that they strike the electrons orbiting the hydrogen protons and strip them away, breaking the atoms back apart into their constituent charged particles. The neutral, light-absorbing fog is being converted back into a transparent, ionized plasma. Around this first star, a bubble of clarity begins to grow, expanding outward into the darkness at nearly the speed of light. It is a sphere of liberation, a zone where light can once again travel freely. For the first time since the universe was 3,800,000 years old, a tiny patch of the cosmos is no longer opaque. Inside this bubble, you could see from one side to the other. It was a minuscule island of transparency in an endless ocean of murk, a single lighthouse in a fog that spanned the entire observable universe. But this star was doing more than just shining. Deep within its thermonuclear heart, it was performing an act of cosmic alchemy that was even more profound than its light. The initial fusion process, the one that ignited the star, turned hydrogen into helium. But as the hydrogen in the core began to run out, the star's life entered a new and frantic phase. Gravity, the relentless engine of creation, squeezed the core even harder. The temperature and pressure soared to new, even more staggering heights, reaching a point where the newly created helium atoms themselves could be forced to fuse together. 3 helium atoms slammed together to form a carbon atom. Add another helium, and you get oxygen. Then neon, magnesium, silicon, and so on, climbing the periodic table in a series of desperate energy-releasing reactions. For the first time in the history of existence, the universe was creating chemistry. This star, this short-lived behemoth, was a factory forging the very elements that would one day become the bedrock of planets, the substance of asteroids, and the raw material for life itself. Every atom of carbon in your body, every atom of oxygen you breathe was forged in the heart of a star, much like this one, though likely of a later generation. These population 3 pioneers were the first to undertake this sacred work. They were transforming the bland, simple, 2-element universe into a place of rich and complex chemical possibility. But this process has a fatal endpoint. The chain of fusion continues until the star's core is filled with iron, and iron is a kind of cosmic ash. Fusing iron atoms does not release energy, it consumes it. The furnace at the heart of the star, the furnace that has held the crushing force of gravity at bay for millions of years, suddenly and catastrophically switches off. In less than a second, the equilibrium is shattered. With its energy source gone, the core collapses under its own stupendous weight. The outer layers of the star, containing thousands of cubic light-years of matter, now have nothing supporting them. They begin to fall inward, rushing toward the center at a quarter of the speed of light. What happens next is not a typical supernova. The sheer mass of a population 3 star triggers one of the most violent forms of stellar death imaginable, a pair instability supernova. The collapsing core becomes so hot and dense that photons transform into pairs of matter and antimatter, robbing the core of the pressure it needs to support itself. The result is total, complete, and utter annihilation. The star does not leave behind a neutron star or a black hole. It is blown to smithereens, vaporized in an explosion of such unimaginable power that for a few weeks it would outshine 1 billion suns. This final convulsive act is the star's true gift to the cosmos. For in that explosion, all the new elements forged in its core, the carbon, the oxygen, the silicon, the iron, are blasted outward into interstellar space. These are the first chemical seeds scattered into the void. The pure primordial gas of the early universe is now in this one location polluted. It is enriched with the building blocks of future worlds. The gas cloud that collapses next in the vicinity of this stellar ghost will not be pure. It will contain those crucial heavy elements, those microscopic radiators that allow the gas to cool efficiently, to fragment, and to form not one single monster but a whole generation of smaller, longer-lived stars. Stars more like our Sunday now zoom out. This incredible story, this cycle of birth, creation, and violent death was not happening in just one place. Across the cosmos, in halo after halo, thousands, then millions of these population 3 stars were igniting, burning fiercely, and exploding. Each one carved its own temporary bubble of transparency in the cosmic fog, and each one seeded its local environment with the first harvest of heavy elements. For a time, the universe would have resembled a block of Swiss cheese. There were dense, dark regions of neutral hydrogen and growing, expanding voids of transparent ionized plasma where the first stars had lived and died. The darkness did not surrender easily. As the short-lived population 3 stars died out, the gas in their bubbles of transparency would often cool and recombine, the fog closing back in. It was a cosmic battle, a tug of war between light and shadow, fought on a galactic scale over hundreds of millions of years. But the tide was turning. The explosions of the first stars triggered new waves of star formation in the enriched gas around them, giving birth to the second generation, the population 2 stars. And these stars began to cluster together, their mutual gravity pulling them into the first recognizable structures, proto-galaxies, small misshapen islands of light burning with the fire of 1,000 suns. The bubbles of reionization began to overlap. What started as isolated pockets of clarity began to connect, forming vast networks and channels through which light could travel across immense cosmic distances. The faint red-shifted light from one fledgling galaxy could now for the first time reach its neighbor. The universe was becoming self-aware, its disparate parts now able to see one another. Slowly, inexorably, the final vestiges of the primordial fog were burned away. The last shadows retreated. The cosmic dark ages, that immense and silent epoch that had defined the universe for so long, were finally definitively coming to an end. The great blank canvas of the cosmos was now illuminated, primed with the chemical elements of creation, and dotted with the first faint lights of infant galaxies. The dawn had arrived, but this was not the end of the story. It was merely the end of the beginning. The stage was now set for an even grander epic, the assembly of the great spiral and elliptical galaxies we know today, the slow and steady enrichment of the cosmos with the elements of life, and the 9-billion-year journey that would eventually lead to a small rocky planet orbiting an unremarkable yellow star in a quiet suburb of the Milky Way. The universe was now ready to build a home, and so the first light had arrived. For 100 million years, a silence of unimaginable depth had owned the cosmos, a darkness broken only by the faint, fading whisper of the Big Bang's afterglow. But now, after an eternity of waiting, something new had ignited within that cold expanse. The first stars, those brilliant, violent titans of pure hydrogen and helium, had finally blazed into existence, tearing a hole in the primordial night. Yet this was not a simple sunrise. The universe was not yet ready to yield its shadows. For every photon that screamed out from these newborn stellar furnaces, a vast, suffocating fog of neutral hydrogen gas stood in its way, an ancient barrier ready to absorb and scatter that precious light into oblivion. Imagine you are standing inside an infinite cloud. You light a match, and for a fleeting moment, a tiny sphere of clarity appears around you, but the light cannot escape. A foot away, the world is still an impenetrable wall of grey. This was the challenge facing the infant cosmos. The arrival of starlight was not the end of the Dark Ages, but the declaration of a war for transparency, a battle to reclaim the universe from the very element that gave it birth. This was the dawn of a new epoch, a chaotic and transformative era of cosmic weather known as the epoch of reionization. The weapon in this war was ultraviolet radiation, a torrent of high-energy photons pouring from those first massive stars. When one of these photons, born in the heart of a star 1,000,000 times brighter than our Sun, struck a neutral hydrogen atom, the effect was instantaneous and profound. It kicked the atom's lone electron completely free, shattering its neutrality and transforming it into a charged plasma of ions. One by one, atom by atom, the light began to win. Around each star, and around the first clusters of stars that would become the seeds of galaxies, a bubble began to grow. Inside this bubble, the universe was clear. It was a pocket of the modern cosmos, a transparent sphere of ionized gas, where light could finally travel freely across immense distances. Outside the bubble, however, the primordial fog remained dense and absolute. This was not a gentle, uniform clearing. It was a violent, patchy, and brutal process of conquest. The cosmos became a battleground of competing frontiers. In regions where gravity had managed to gather more dark matter, more gas was available to collapse, forming dense nurseries of these population 3 stars. In these over-dense regions, the bubbles of ionization grew rapidly, powered by the combined fury of dozens, even hundreds of short-lived stellar behemoths. These bubbles swelled like celestial balloons, their luminous interiors pushing back against the dark, neutral territory of the intergalactic medium. They were islands of light in an endless ocean of night, oases of clarity in a universe still shrouded in mist. And as these bubbles expanded, they began to encounter one another. The frontiers of 2 separate ionized zones would meet their shockwaves, colliding and merging, creating ever larger, more complex clearings in the cosmic fog. For hundreds of millions of years, the universe would have looked like this, a cosmic foam of incandescent bubbles growing within a vast, dark structure. If you could have witnessed it, you would have seen a spectacle of unimaginable scale, a creeping dawn that advanced not as a single wave, but as a spreading luminous infection consuming the darkness from within. Some regions would be fully illuminated, blazing with the trapped light of their stellar engines, while just a few million light-years away, the universe remained as dark and cold as it had been since the beginning. But the first stars were celestial martyrs. They burned hot, and they died young, exploding in cataclysmic supernovae after only a few million years. While their death seeded the cosmos with the first heavy elements, their light would have flickered out, allowing the fog to reclaim its territory. If stars were the only actors in this drama, reionization might have been a long, sputtering, and perhaps even failing endeavor. The universe needed bigger engines. It needed more persistent, more powerful sources of radiation. And as the first stars died, they left behind monstrous relics, the first black holes. In the churning, chaotic hearts of the most massive protogalaxies, these black holes began to feast. Gas pulled by their inescapable gravitational grips spiraled inwards, forming accretion disks of unimaginable temperature and brightness. As matter was torn apart at the event horizon's edge, it released energies that dwarfed even the most massive stars. These were the first quasars' celestial blowtorches of almost incomprehensible power, blasting the cosmos with torrents of X-rays and ultraviolet light. A single quasar could outshine its entire host galaxy, a luminous spear thrown into the heart of the remaining darkness. The light from these quasars carved out colossal new bubbles of ionization far larger and more energetic than those created by stars alone. They became the lighthouses of the early cosmos, their beams slicing through the fog for hundreds of millions of light-years. The war for transparency had just gained its heavy artillery. Now the process of reionization accelerated dramatically. The bubbles grew faster, merged more violently, and the remaining pockets of neutral hydrogen found themselves besieged from all sides, illuminated and eroded by the relentless radiation from these new galactic-scale beacons. This onslaught of energy from both the second generation of stars and the ravenous black holes at their core did more than just burn away the fog. It fundamentally reshaped the cosmic landscape in a process we call feedback. The early universe wasn't just being illuminated, it was being sculpted. The intense radiation streaming out from the first galaxies heated the intergalactic medium, the vast diffuse gas that existed in the voids between them. Before reionization, this gas was cold, perhaps only a few degrees above absolute zero. After it was superheated to tens of thousands of degrees. This heating had a profound and paradoxical consequence. Cold gas is the fuel for star formation. It is fluffy, compliant, and easily persuaded by gravity to collapse into the dense clumps that ignite as new stars and galaxies. Hot gas, however, is a different beast entirely. It is pressurized, energetic, and it resists the gentle pull of gravity. The very radiation that cleared the cosmic fog also acted as a sterilizing agent. It raised the so-called Jeans mass, the minimum amount of matter required for gravity to overcome thermal pressure and initiate collapse. Suddenly, for small, dwarf-sized halos of dark matter, the game was over. Even if they contained enough gas, they no longer possessed the gravitational might to hold onto it. The heated gas simply boiled away, expanding back out into the intergalactic medium, their potential to form stars extinguished forever. We see the ghosts of this process today in the missing satellite problem, the strange scarcity of small dwarf galaxies orbiting our own Milky Way. It's possible we are seeing the ancient consequences of feedback, the cosmic infant mortality inflicted by the light of the first giants. The dawn it turns in had a dark side. It was a period of creation and destruction, where the birth of the first large galaxies came at the cost of suppressing the formation of countless smaller ones. But feedback wasn't merely destructive. It was a cosmic sculptor's tool working on both grand and intricate scales. While it sterilized the voids and stunted the growth of cosmic dwarfs, the same powerful outflows of energy and radiation could have the opposite effect elsewhere. The shockwaves from supernovae and the powerful jets from quasars acted like immense galactic-scale pistons. As they slammed into the surrounding medium, they could compress vast clouds of hydrogen gas, pushing them past the critical density needed for collapse and triggering furious new bursts of star formation. The universe was sorting itself out, establishing a new order. The rich were getting richer as the largest gravitational wells captured more gas and ignited with ever greater brilliance, while the poor had their stellar fuel stripped away, their futures dimmed before they could even begin. This process created the very foundations of the cosmic web we observe today. The universe is not a uniform sea of galaxies. It is a tapestry of filaments, clusters, and voids. The filaments are the grand highways of cosmic matter, rivers of gas and dark matter flowing across billions of light years, and at their intersections we find the great clusters, the metropolises of the cosmos. The voids, in contrast, are immense, nearly empty deserts. This structure was seeded by the Big Bang, but it was sharpened, defined, and chiseled into its modern form by the feedback of the reionization era. The outflows and radiation pressure pushed gas out of the less dense regions, evacuating the voids, and shepherded it onto the filaments, providing the raw material for the next generation of galaxies to be built. How can we be so sure of this violent, transformative history? We can't travel back in time to witness it, but we have learned to read its echoes in the light of the most distant objects we can see. When we point our telescopes at a quasar billions of light years away, its light begins a long journey toward us. For billions of years it crosses the expanding universe, and on its way it passes through the vast clouds of hydrogen gas that still linger in the intergalactic medium, the very remnants of that primordial fog. Each time the quasar's light passes through a cloud of neutral hydrogen, a specific wavelength of that light is absorbed, creating a dark line in its spectrum. By the time the light reaches us at the Keck Observatory or on the mirrors of the Hubble and James Webb Space Telescopes, its spectrum is no longer a smooth continuum of color. It is a dense thicket of thousands of these absorption lines, a barcode of cosmic history. We call this the Lyman Alpha Forest. Each tree in that forest tells us where a cloud of neutral gas existed along our line of sight and how much there was. By studying the Lyman Alpha forests of countless distant quasars, we can build a three-dimensional map of the gas in the early universe. And what that map shows us is extraordinary. When we look at the light from the most distant quasars, those whose light has traveled for over 12.5 billion years, the forest is incredibly dense. So many of the photons have been absorbed that it's almost a solid wall of absorption, a Gunn-Peterson trough. This is the unmistakable signature of a universe still largely filled with that neutral light-absorbing fog. It is the fossilized evidence of the Dark Ages imprinted on the oldest light in the cosmos. But as we look at slightly closer quasars from a time just a few 100 million years later, we see the forest begin to thin out. Patches of transparency appear. The dark lines become more distinct, separated by regions of clear, unabsorbed light. We are quite literally watching the bubbles of reionization. We are seeing the moment in cosmic history when those islands of clarity were growing and merging, allowing more and more light to punch through the fog. This cosmic barcode allows us to survey the final stages of that ancient war for transparency, to watch the last vestiges of the neutral fog being burned away by the relentless onslaught of ultraviolet radiation. It is one of the most profound achievements in modern cosmology, using the light from the universe's brightest beacons as cosmic flashlights to probe the shadows of its own dawn. Slowly, inexorably, the balance of power shifted. The bubbles of ionization, once isolated pockets in a sea of darkness, swelled and merged until they became the sea itself. The last remaining islands of neutral gas, besieged from all sides, finally evaporated under the unceasing radiative pressure. The war was over. The fog had lifted. For the first time, from one end of the visible cosmos to the other, the universe was transparent. Light was no longer a prisoner, but a traveler free to journey across billions of light years, to carry the story of distant stars and nascent galaxies to any observer who might one day exist to see them. This momentous transition, completed roughly 1 billion years after the Big Bang, marked the true end of the cosmic dark ages. The universe was now bathed in starlight. It was hot, ionized and clear, but the cosmos that emerged from this epoch was a vastly different place from the one that had entered it. It was a universe that had been fundamentally re-engineered. Its matter had been rearranged, its evolution had been irrevocably altered, and the stage had been set for the next even grander act of creation. The great cosmic web had been woven and defined its filaments, charged with the fuel for the future. The great galaxies we know and love, the spirals, the ellipticals, the grand designs, did not yet exist. But now, in this newly transparent and sculpted universe, they finally could. The age of structure was about to begin. For generations, this epic of the cosmic dawn was a story confined, a grand narrative told only in the silent language of mathematics, a ghost story whispered between the circuits of supercomputers. It existed as a beautiful, compelling, but ultimately unproven idea, a history of the universe with its most crucial chapter left blank, waiting for an author who could bear witness across 13 billion years. To truly know our origins, to ground our cosmic story in reality, we had to achieve what seemed a physical impossibility. We had to invent a way to see in the dark. We had to build a time machine. And we did. Not a machine of gears and chrome, but of gold and light. The James Webb Space Telescope is humanity's audacious attempt to capture the most ancient, most fragile photons in existence. It is the culmination of decades of dreaming, a magnificent golden eye unfolded in the chilling void a million miles from Earth. Every element of its design is a solution to a colossal problem: how to see the ephemeral light of the universe's very first stars. Its iconic honeycomb of 18 hexagonal mirrors, each polished to a precision of a few dozen atoms, is coated in a microscopically thin layer of pure gold. This isn't for aesthetics. Gold is a near-perfect reflector of the specific kind of light we seek: long wavelength infrared, the ghost light of the early cosmos. To see these faint signals, the telescope itself must be fantastically cold, colder than any natural place on the surface of the Earth. Shielded by a 5-layered sunshield the size of a tennis court, Webb operates in a perpetual shadow, a mere 40 degrees above absolute zero. At this temperature, its own heat signature all but vanishes, preventing the telescope from blinding itself with its own glow, allowing it to hear the faintest whispers from the dawn of time. The reason for this extreme sensitivity, this obsession with the infrared, lies in the very nature of our expanding universe. The light from those first trailblazing galaxies began its journey as a searing, brilliant, ultraviolet glare, the light of titans. But for over 13.5 billion years, it has been traveling, racing toward us across an ever-stretching fabric of space-time. As space itself expanded, it stretched these waves of light along with it, pulling them, shifting their color like a siren's note dropping in pitch. Ultraviolet became visible light. Visible light became infrared. The brilliant song of creation was redshifted into a deep thermal hum, rendering it completely invisible to the human eye and even to the legendary gaze of the Hubble Space Telescope. Webb was built to see this stretched, tired, ancient light. It is a cosmic archaeologist's brush, designed to gently sweep away the dust of ages and reveal the foundations of galactic structures. And when its first images were finally gathered and released, humanity held its collective breath. In a tiny sliver of sky, a patch so small it represents what you would see, holding a single grain of sand at arm's length. The telescope stared, gathering photons for days on end. The result was not a picture of the Dark Ages themselves, but something arguably even more profound. It was a snapshot of the very end of that era. Before you, in these breathtaking deep-field mosaics, is a portrait of the universe in its turbulent adolescence. Among the familiar, magnificent spiral galaxies of the nearer cosmos, your eye is drawn to the smudges, the tiny, misshapen specks of red. These are not single stars, they are not local objects. Each one of those faint crimson dots is an entire nascent galaxy, its light having traveled for more than 13 billion years to reach us. We are seeing them as they were just a few 100 million years after the Big Bang itself. These are the lighters. These are the engines of reionization. For the first time, we are not simulating or guessing. We are seeing times the agents of change. These infant galaxies are chaotic, clumpy, and intensely bright, burning with a ferocity that modern galaxies can no longer muster. Within them, millions of the first and second generation of stars are being born in violent, compressed nurseries. They are the celestial blowtorches that began to burn away the cosmic fog, the sources of the ionizing radiation that fundamentally re-engineered the cosmos. In Webb's data, we can see how they cluster, how they grow, how they begin to form the very first threads of the cosmic web. The story that was once pure theory is now being written in photons collected by a golden mirror floating in the deep cold of space. We have found the first page of the chapter we thought was lost forever. Yet seeing the lighters is only half the story. To truly understand this epoch, you must also see the darkness they conquered. You must map the great ocean of hydrogen gas they set ablaze. Seeing the galaxy's Webb finds is like seeing a few scattered campfires at night from a high mountain. You can see the points of light, but you know nothing of the vast unseen landscape that lies between them. To chart that landscape, we needed a completely different kind of eye. We needed an ear. We needed to learn how to listen to the silence itself. The key was a whisper, a signal so subtle and pervasive it was predicted decades before we had any hope of detecting it. It's called the 21 centimeter line or the hydrogen line. It is not the light of stars, but the murmur of the universe's most common element. Throughout the Dark Ages, the cosmos was overwhelmingly filled with cold, neutral hydrogen gas, a single proton orbited by a single electron. In quantum mechanics, both of these particles have a property called spin. Occasionally, and with incredible rarity for any individual atom, the electron will spontaneously flip its spin relative to the proton, moving from a slightly higher energy state to a slightly lower one. When it does, it releases a tiny, precise puff of energy, a radio wave with a wavelength of exactly 21.1 centimeters. This is the universe's fundamental hum. A single atom might emit this photon only once every 10 million years, but during the Dark Ages, there were unimaginable trillions of these atoms, filling every cubic meter of an expanding universe. The cumulative effect was a faint, ever-present background glow, a fossil radio wave permeating all of space, and encoded within it is everything. The temperature of the gas, its density, its distribution, it's all written in the strength and character of that 21 centimeter signal. It is a three-dimensional map of the dark universe. If we could only detect it, we could watch the Dark Ages unfold. We could see the first stars ignite not by their own light, but by the way their radiation warmed and agitated the gas around them. We could watch in silhouette as the bubbles of ionization grew and merged. We could create a time-lapse movie of the entire epoch of reionization. It stands as one of the single greatest observational challenges in the history of science. The problem is noise. That primordial signal stretched by cosmic expansion over billions of years to wavelengths of several meters is catastrophically faint. It is buried, drowned out by a cosmic cacophony 100,000, even 1,000,000 times louder. Our own Milky Way galaxy screams in the radio spectrum, a foreground blaze of synchrotron radiation from electrons spiraling around magnetic fields. Distant galaxies and quasars add to the din. And here on Earth, our own technological civilization is a beacon of radio noise. Every television broadcast, every mobile phone call, every spark plug is a source of contamination that can utterly swamp the ancient signal. Trying to detect the 21-centimeter line from the Dark Ages is like trying to hear a single bee buzzing in another country while standing next to the stage at a rock concert during a thunderstorm. To even attempt this feat, we had to reinvent the very idea of a telescope. A single giant dish wouldn't work. It would be deafened by the overwhelming foreground noise. Instead, astronomers conceived of a new kind of observatory, the low-frequency radio interferometer. These are not elegant, soaring structures. They look more like strange metallic forests planted in the most remote, radio-quiet places on the planet. In the Netherlands, the low-frequency array, or LOFAR, spreads thousands of simple stationary antennas across northern Europe, linked by fiber optics into a single continent-spanning digital sensor. In the deserts of Western Australia, the Murchison Widefield Array, or MWA, consists of thousands of spider-like antennas arranged in precise grids, and in the silent Karoo Desert of South Africa, the Hydrogen Epoch of Reionization Array, or HERA, uses a fleet of 14-meter dishes that stare unblinkingly at a single patch of the sky, letting the Earth's rotation do the scanning for them. The strategy for these cosmic ears is one of immense patience and brute force computation. They stare at the coldest, quietest patches of the sky regions, away from the blinding plane of the Milky Way, for thousands upon thousands of hours. They don't form an image in the traditional sense. Instead, they measure the statistical properties of the radio waves they receive. Supercomputers, among the most powerful on Earth, then begin the Herculean task of digital signal processing. They must create a perfect model of the galactic foreground, this wall of radio noise between us and the early universe, and then subtract it from the data with surgical precision. They must identify and excise every sliver of human-made interference. What is left over after this painstaking process of digital purification is hopefully the prize, the faint statistical hum of primordial hydrogen. For years, the teams worked in a state of tense anticipation. The data flowed in terabytes upon terabytes every single night. The analysis was a slow, meticulous process of eliminating one source of error, one source of contamination after another. Then the first hints began to emerge. A tentative detection of the cosmic dawn suggesting the gas was colder than our simplest models had predicted. A statistical whisper from the MWA, pointing towards the characteristics of the universe, just as reionization was getting underway. These were not yet the beautiful maps we dream of, not the cinematic movie of a universe being born. They were subtle signatures buried deep within the noise, the first glimmers of a revolutionary new view of the cosmos. The community is electrified. The veil is beginning to tremble. We are on the cusp of confirming a story once told only by theory. But to fully part that veil, to transform these statistical hints into a crystal clear picture, requires a tool of an even grander scale. An instrument so vast, so powerful, it is being built across 2 continents. The Square Kilometre Array, or SKA. When complete, it will be the largest scientific instrument ever constructed on Earth. In South Africa, nearly 200 dishes will join the existing Meerkat Array, creating a mid-frequency telescope of unparalleled sensitivity. And in the remote desert of Western Australia, over 130,000 Christmas tree-like antennas will be spread across hundreds of kilometers. The SKA will not just be an ear. It will be a global nervous system, its thousands of individual sensors connected by a fiber optic network, carrying more data than the entire internet traffic of planet Earth. Its computational power will be staggering, required to correlate the signals from every antenna with every other antenna in real time. With this monumental instrument, we will finally do more than just detect the signal. We will map it. The SKA will have the sensitivity and the resolution to create a full three-dimensional tomographic survey of the dark ages and reionization. We will be able to tune through different frequencies which correspond to different cosmic distances and therefore different times, like tuning a radio dial through history. At one end of the dial, we will see the cold, uniform hydrogen fog of the dark ages. As we tune further, we will begin to see dark patches appear, not darkness as in the absence of light, but darkness in the 21 cm signal. These are the bubbles, the regions where the first stars have ignited, and their fierce radiation has ionized the hydrogen, rendering it transparent and silencing its 21 centimeter hum. We will be able to watch over 1 billion years of cosmic history compressed into a stream of data as these bubbles grow. We will see them expand, merge, and overlap until finally the last vestiges of the neutral fog are burned away and the universe transitions into the transparent, star-filled cosmos we know today. This is the holy grail of observational cosmology, a direct film of the universe's most profound transformation. We will pinpoint where and when the first stars lit up. We will measure the properties of these population 3 stars, not by their own light, but by the indelible footprints they left on the cosmic gas around them. This will no longer be a story, it will be an observation, an atlas. And here, in this dual approach, lies the true power of our new vision. The James Webb Space Telescope gives us the portraits of the protagonists. It finds the brilliant concentrated sources of light, the galactic seeds that drove this monumental change. Its infrared eyes deliver the stunning visceral evidence of the actors themselves. The radio arrays culminating in the SKA provide the context. They draw the map of the stage, the ghostly diffuse canvas of gas upon which this drama played out. One method gives us the cause, the other reveals the effect. One gives us the photograph, the other gives us the environment. Together, they are like 2 new senses working in concert to build a rich, multi-layered perception of a time and place we can never visit. For the first time in human history, we are no longer looking out into a universe where the earliest chapters are sealed. The fog is beginning to clear. The silence is beginning to speak. We are developing the senses to perceive the cosmos in its entirety, from the first flicker of starlight to the grand celestial architectures of today. The veil that has shrouded the dawn of time for 13 billion years is finally lifting, and what we are beginning to see on the other side is proving to be more complex, more surprising, and more magnificent than our theories had ever dared to imagine. The age of cosmic archaeology has truly begun, and so our journey through the deepest night comes to a close. We have travelled back across more than 13.5 billion years past the familiar glow of the nearest stars, beyond the swirling arms of our own Milky Way, and past the most distant galaxies ever photographed. We have pushed our understanding to the very edge of the visible, to a time when the entire universe was a fading ember, the afterglow of creation itself. From that final fading light of the cosmic microwave background, we plunged with the cosmos into an abyss of absolute unrelenting darkness, an era of silence, an epoch defined not by what was, but by what was not. There were no stars to pierce the gloom, no galaxies to spin in majestic silent ballets. There was no light. This was the great cosmic intermission, a period stretching for hundreds of millions of years, an age cloaked in a veil so profound that for generations it remained a blank page in our cosmic story. But we have learned that this darkness was not an emptiness. It was not a void. It was a crucible. It was the vital formative stage in which the universe we know today was conceived. Within that pristine blackness, the quietest and most powerful force in existence was patiently at work. Gravity, the universe's master architect, began its slow, inexorable labor. It gathered the invisible threads of dark matter, weaving them into a vast, unseen scaffolding that would eventually dictate the location of every galaxy and every star cluster. These dark matter halos, growing like ghostly crystals in the primordial soup, became the gravitational anchors, the cosmic basins into which ordinary matter, the endless ocean of hydrogen and helium atoms, would begin to pool. You must imagine the scale of this construction, Over millions of years, in the chilling silence, these atoms, which had been spread with almost perfect uniformity, answered gravity's call. They trickled, then flowed, then cascaded into the deepening wells of dark matter, forming clouds of gas more vast and more pure than anything that exists today. This was the universe holding its breath, gathering its strength for the cataclysm of creation that was to come. Every structure we now observe, from the smallest dwarf galaxy to the most colossal supercluster, has its origin story written in these subtle gravitational currents that flowed through the dark. The darkness was not just a nursery for structure, it was the stage for the universe's first great act of alchemy. When the density within the largest of those primordial clouds reached a critical tipping point, a new kind of fire was lit. Not the fading fire of the Big Bang, but a focused, furious nuclear furnace. The population 3 stars ignited. These were not stars as we know them. They were titans, behemoths of pure hydrogen and helium, hundreds of times more massive than our own sun, and millions of times brighter. They were celestial blowtorches that lived fast and died young, burning through their fuel in a cosmic heartbeat. But in their brief, impossibly violent lives, they performed a miracle. Inside their cores, under unimaginable pressure and temperature, they fused the first simple elements into heavier ones: carbon, oxygen, nitrogen, silicon, iron. For the very first time, the universe was creating the raw materials for complexity, the atomic building blocks of planets, of atmospheres, and ultimately of life itself. Their deaths were as significant as their lives. When these Goliaths exploded as the first supernovae, they scattered these newly forged elements across the surrounding space, like a celestial sower casting seeds. This enrichment was a pivotal moment of no return. The universe was no longer a simple two-element system. It was now seeded with potential. Every subsequent generation of stars, including our own sun, would be born from these enriched clouds. The planets in our solar system would be built from this stellar dust. The very iron in your blood, the calcium in your bones, the oxygen you are breathing at this very moment, was forged in the heart of a long-dead star that was born in the aftermath of that first great dawn. The Dark Ages, therefore, are not a distant abstract chapter in cosmic history. They are the bedrock of our own material existence. They connect us in the most direct and profound way to the very beginning of cosmic structure and chemistry. Without that long period of quiet gravitational assembly and that first violent generation of stellar alchemists, we simply would not be here. The universe would have remained a sterile, uninteresting expanse of simple gas forever dark. Understanding this formative epoch is now one of the grandest challenges in all of science, a true frontier of human knowledge. How do you observe an era defined by the absence of light? How do you map a time before there was anything to map? The answer lies not in seeing but in listening. We are striving to hear the whispers of that ancient hydrogen gas, the most abundant element in the cosmos. We are hunting for a specific faint signal, a ghostly radio wave with a wavelength of 21 centimeters. This is the natural frequency at which a hydrogen atom can flip the spin of its electron, releasing a tiny, almost imperceptible puff of energy. During the Dark Ages, the entire universe was filled with these atoms, and the collective whisper of their spin flips created a faint background hum, a kind of cosmic static that encodes the story of that era. It is the only direct messenger we have from the deepest night, a fossil record of the universe before the first star ever shone. Detecting this 21 centimeter signal is an undertaking of staggering difficulty, an effort that pushes our technology and our ingenuity to their absolute limits. The signal has been traveling for over 13 billion years, and in that time the expansion of the universe has stretched it, weakening it, redshifting it into a faint murmur. It is now buried beneath a cacophony of cosmic noise. The radio emissions from our own Milky Way galaxy are hundreds of thousands of times louder. The radio chatter from our own civilization, our phones, our satellites, our televisions, is a billion times stronger. It is the ultimate search for a needle in a galactic haystack. To find it, we are building gargantuan ears radio telescopes of unprecedented scale and sensitivity. In the quietest, most remote deserts on Earth, places like the Australian outback and the South African Karoo, arrays of thousands of antennas are being constructed. Projects like the Square Kilometre Array are not merely telescopes, they are planetary-scale instruments, designed to sift through the cosmic noise with breathtaking precision, hoping to isolate that one faint elusive tone from the dawn of time. This monumental effort is a race against our own noise. Every new satellite launched, every new broadcast tower erected, makes the task of listening to the universe's infancy that much harder. We are in a unique, perhaps fleeting moment in history where we have the technological capability to detect this signal, but have not yet completely deafened ourselves to it. While these radio astronomers listen for the prelude to the dawn, other explorers are attacking the problem from the opposite direction. Telescopes like the James Webb Space Telescope are our time-traveling eyes, powerful enough to peer back to the very end of the Dark Ages. They cannot see into the darkness itself, but they are capturing the light from the very first galaxies to ignite, witnessing the moment the cosmic dawn broke and the era of reionization began. They are seeing the final act of the drama. By combining what we see from the end of that era with what we hope to hear from its beginning and its middle, we are slowly, painstakingly beginning to triangulate the truth. We are piecing together the complete narrative, illuminating the darkness from both ends of the timeline, bridging the gap between the universe's baby picture in the cosmic microwave background and the star-filled cosmos we inhabit. Today, the quest to fully understand the Dark Ages is in its essence a quest to understand our own origins in the most fundamental way imaginable. It forces us to confront the profound truth that everything we see, everything we are, emerged from a state of near-perfect simplicity and blackness. The universe did not begin complex. It earned its complexity through the slow, patient, and sometimes violent processes that unfolded during that first billion years. The darkness was not a failure of the universe. It was a necessary feature. It was the quiet canvas upon which gravity could paint its masterpiece. It was the silent stage upon which the first stars could perform their transformative act. It was the womb in which the potential for galaxies, planets, and life was nurtured. We are the direct descendants of that darkness. The starlight that reaches your eyes on a clear night began its journey thousands or millions of years ago. But the story of that light, the story of the star that created it, began in the unseen collapse of a hydrogen cloud in the aftermath of the universe's first night. Our exploration of this era is a testament to the relentless nature of human curiosity. We are a species that cannot tolerate a blank page in our history. We build these extraordinary machines, these technological cathedrals to science, to answer a question that is as simple as it is profound. Where did all of this come from? The secrets still locked away in that primordial epoch are immense. What were the first black holes really like? How exactly did they grow to become the supermassive giants that now sit at the heart of every major galaxy? Was dark matter entirely passive, or did it have properties that influenced the birth of the first stars in ways we don't yet understand? Did reionization happen smoothly and uniformly, or was it a messy, patchy process, with bubbles of light expanding and battling against the retreating darkness for millions of years? Answering these questions will not just fill in the details of our cosmic story, it will fundamentally refine our understanding of the laws of physics and the evolution of the entire universe. We stand today on the precipice of a new era of discovery. We are the first generation of human beings with the tools and the ambition to shine a light into that foundational darkness. For all of recorded history, the time before stars was a realm of pure speculation, a domain for mythology and philosophy. Now it is becoming a landscape we can map, a history we can read. The journey is far from over. The challenges are formidable, but the promise is nothing less than a complete understanding of our cosmic genesis. We continue to listen, to watch, to search for those faint, ancient signals, driven by the knowledge that the answers to our deepest questions about who we are lie hidden in the silence and the dark. The universe, it seems, had to pass through its longest night before it could awaken, and we, the inheritors of that awakening, have only just begun our quest to understand the profound and beautiful mystery of the dawn.